Hello. Since we have almost finished discussing ultraviolet and visible spectroscopy of organic compounds, uh, we are today going to start learning a few details about the infrared spectroscopy. That means the vibrational spectroscopy of organic molecules. So first we are going to freshen up a little bit about the basics. Okay, so when a molecule absorbs a radiation, that happens when the energy gap between the corresponding energy levels, okay, be it electronic, vibrational or rotational energy levels, once the energy gap between the initial energy level and the final energy level, E or delta E is equal to h nu, where h is the Planck's constant and nu is the frequency of the incoming radiation. So under this condition, the molecule can interact with the radiation, usually the electric field of the radiation, and as a result, the molecule can get excited from the lower energy level to upper energy level. So this is also the same principle for vibrational spectroscopy. Okay, but unlike or compared to electronic or rotational spectroscopy, here the transition happens between vibrational energy levels. I hope you remember the relationship between energy, frequency, wavelength, and wave number. I'm not going to discuss or draw in this particular slide a lot, so I'm just going to skip this one, assuming that you know this relationship, or assuming that you remember these relationships, and you must be knowing this as well, but I'm just going to brush up a bit here. Here the radiation is being expressed in terms of the frequency or energy or wavelength or wave number, and as you can see, the gamma rays lies on the lower wavelength region of the spectrum, and it has got the highest energy, and the radio waves lies on the longer wavelength of the spectrum, and the radiation has got the lowest energy out of all these radiations. And we have already discussed about UV and visible spectroscopy, where we usually discuss about electronic excitation or electronic transitions in organic molecules. And right now what we are going to discuss about infrared spectroscopy, where the energy frequency varies from say around 10 to the power 14 to approximately 10 to the power 10 hertz, and wavelength ranges from something like a almost 800 nanometer up to, say, for example, 3500 nanometer, and the energy in kilocalories per mole varies from, say, approximately 300 kilocalories per mole up to almost 700 kilocalories per mole. So this is the region where we are mostly interested in, and in this particular region the radiation has got enough energy to induce vibrational transitions in organic molecules. So we are going to see how that happens. And here, say for example, if you consider a diatomic molecule having a heavier nucleus on one side and a lighter nucleus on the other side, which is bound by a covalent bond in between, and this molecule obviously has got 0 point energy at room temperature, but once the molecule starts to interact with an infrared radiation, what happens is the molecule could absorb the radiation provided that delta E is equal to h nu. But how does this happen? Okay, so consider the vibration of a molecule, okay, like the vibration of an oscillating spring. Okay, so you assume that the molecule vibrates like an oscillating spring. So what happens is there could be several vibrations in molecules, and the bond vibrations can be classified into two categories: stretching vibrations and bending vibrations, which you have already seen. And stretching could be either symmetry vibrations, which involves symmetric stretching of or symmetric compression of the involved chemical covalent bonds, and asymmetric stretching where the one of the bonds stretches out while the other bond compresses in. And the bending vibrations could be either scissoring vibrations, just like in the case of the legs of a scissor, a pair of scissors move, and then the rocking vibrations where you have seen in concerts people rock their hands to either sides in when the music plays. So such kind of vibration motion is called rocking motion, and this one is a rocking vibration. And there could be these two vibrations are in plane vibrations, bending vibrations, and there could be two out of plane vibrations, the twisting vibrations and the wagging vibrations. Okay, so these are the basic categories of vibrations, bond vibrations a molecule can have when it interacts with an infrared radiation. So but how does this happen theoretically? So you could assume a classical picture in which the vibration of a diatomic molecule having dissimilar type of nuclei on either sides of the covalent bond. So this vibration should in principle generate an electromagnetic field of having some kind of sinusoidal character. Okay, so this electromagnetic field generates out of the fact that these two nuclei should be of different electronegativities. So essentially that should generate a dipole moment between the dipole moment between the both the nuclei. And when the bond vibration happens, what happens is the internuclear separation varies, and with the variation of the internuclear separation, the magnitude of the dipole moment varies, and the magnitude of the dipole moment varies in a sinusoidal fashion. That's how we represent the variation in the electromagnetic field that is being produced by the variation of the the electric dipole moment of the molecule. Okay, so this varying electric dipole moment or the electromagnetic field that is being generated out of the vibration. Okay, so what happens is when such a molecule encounters an infrared radiation having a particular electromagnetic field, having an electric field which vibrates with a particular frequency, okay, and a particular amplitude. Suppose such a vibrating diatomic molecule, when it encounters an infrared radiation which has got an electric field having a sinusoidal character such as this one, and once the molecule encounters such a radiation, so if the amplitude and the phase of the infrared radiation or the electric field of the infrared radiation, if it matches with the amplitude and phase of the electric field generated by the diatomic vibration here, then we can say that we have got a resonance condition here where both the waves can mix with each other, generating a coupled wave with a almost twice the amplitude, since both the waves under resonance, since both the waves have got the same amplitude, almost the same amplitude. Okay, so this wave is being detected in IR spectroscopy, and this wave generates the IR signal. Okay, and we have seen the basics of how this IR spectrum can be acquired in our second semester classes. So what happens is, when we put a sample in the path of an IR beam, infrared beam, the molecule could absorb the infrared beam depending upon the bond stretching vibrations or bond bending vibrations and its energies. So suppose that when we put a sample in an IR beam, one of the bonding vibration one type of bonding vibration, whether it is stretching or bending vibration, when it absorbs the radiation, what happens is some part of the radiation is being absorbed by the sample, and the rest of the radiation is being transmitted by the sample. Okay, so in IR spectroscopy we measure the percentage of transition, the percentage of the radiation that is being transmitted after absorption by the sample. Okay, so in the IR spectrum we plot percentage transmittance on the y-axis. Okay, starting from 0 to 100 centimeter 100 percentage. Okay. So here we have percentage transmittance, and on x-axis we have got energy, which is being plotted in terms of centimeter inverse, because in IR spectroscopy we conventionally use the scale of centimeter inverse, okay, for some traditional reason. Because one of the advantage of using the scale, the unit in centimeter inverse, is that the wave number scales linearly with energy. Okay, so that is one of the reasons. So what happens is, at some particular energy, say for example 3380 centimeter inverse, some type of stretching or bending vibration can happen in the molecule. So in order for this vibration to happen, the molecule should absorb some IR radiation that is coming on the pathway of the sample. Okay. So the molecule absorbs the radiation. So when the molecule absorbs the radiation, the light that is being transmitted, the amount of light that is being transmitted will get reduced from 100%. Okay. So this is what happens. So initially, we scan, or the detector of the, or the monochromator of the IR spectrometer scan from, say for example, to almost 200-500 centimeter inverse, that means right here, towards 4000 centimeter inverse. Okay. So as it scans, the percentage transmittance is almost 100%. That means the molecule is not absorbing much of the IR radiation. That means there is no vibrational transition happening. But as we scan towards this region, what happens is the transmittance gets reduced. That means the molecule starts to absorb the IR radiation, and some sort of vibration is happening, bond vibration is happening in the molecule. Okay. So again, after some point, the transmittance goes back to the almost up to around 80%. That means the energy, the molecule has passed the required energy for typical vibration to happen. Okay. Then again, what we see is, once we scan towards this region, we see a drop in the transmittance. That means the molecule starts to absorb the IR radiation again. So this time the absorption of the IR radiation happens at a different energy. That means the molecule is absorbing an IR radiation having a different energy compared to the IR radiation that is being absorbed right here. So that means a different type of bond vibration starts to happen in the molecule. Okay. So again, what happens is, after, when we scan beyond this particular point, the transmittance increases and reaches almost more than 90%. That means the molecule is no longer absorbing the IR radiation for vibrations to happen. So this is how we get the peaks in IR spectroscopy. So each of these peaks corresponds to some sort of different types of vibrational motions or vibrational transitions in the molecule. So why are we interested in taking the IR spectrum of organic molecules? Because these bond vibrations are actually influenced by the type of bonding between the nuclei that forms a chemical bond or a covalent bond, and the nature of the nuclei, whether the one of the nuclei is more electronegative compared to the other nuclei that forms a chemical bond with the first nuclei, or one of the nuclei is heavier compared to the other nuclei. These factors basically, you can say that the vibrational motions are in fact a function of the type of nuclei in a molecule, as well as the type of bond between the nuclei in a molecule. Okay. So overall, you can say that the vibrational frequencies or vibrational energies are a function of the chemical structure. Okay. Essentially, chemical structure is a structure which consists of nuclei and the bonds, right? So the vibrational features or vibrational energies are a function of the chemical structure of the molecule. So that makes the IR spectrum attractive. The IR spectra of a molecule can tell some details about the molecular structure of a molecule. So usually, you know that if you apply the classical spring model to the vibrating molecule, then you can approximate the vibrational frequency to the force constant of the chemical bond that is being involved in vibrational transition, or vibrational motion, as well as the reduced mass of the nuclei that forms the chemical bond that undergoes vibration, right? So this is given by the famous equation nu is equal to 1 by 2 pi into square root of k by mu. Okay, so where k is the force constant and mu is the reduced mass. Okay, so that means the vibrational frequency is directly proportional to the force constant of the bond, and vibrational frequency is inversely proportional to the reduced mass of the nuclei that forms the chemical bond. Okay, so this means that lighter atoms will facilitate a high frequency oscillation or higher energy vibrational motion, right? Because when lighter atoms are involved in forming a chemical bond, the reduced mass of the nuclei that forms the bond gets decreased, right? So the reduced mass decreases. So since reduced mass is inversely proportional to frequency, with a decrease in reduced mass, the vibrational frequency increases. That means the vibrational frequency can be observed, or vibrational transition can be observed at a higher frequency or higher energy. Okay, this is especially true for chemical bonds that involves hydrogen atom, for example CH, NH and OH. So you can just work this out. Okay, so for example, if you compare CH bond to carbon CC bond, okay, you can say that the reduced mass of the CH bond will be lesser compared to the reduced mass of the CC bond. Okay, so this makes the CH oscillation much more to happen at a higher frequency compared to the CC oscillation. So this is a basic principle. And higher frequency means higher wave number. Okay, so that's what we mean in IR spectrum. So that means around towards higher wave number. Again, the vibrational frequency is directly proportional to the force constant of the chemical bond. Okay, and as you know that triple bonds have a higher force constant compared to double bonds, which has got a higher force constant compared to double bond. Obviously the bond order influences the force constants. Okay, so for that reason, triple bond vibrations happens at a higher frequency or higher wave number compared to double bond oscillations. Okay, and double bond vibrations happens at a higher frequency or higher wave number compared to single bond vibrations. Okay, so this is generally true for these type of bonds or bond patterns in organic molecules. Okay, so what does actually affect the intensity of IR peak or a peak in an IR spectrum? Okay, so one of the reason is that whether the vibration is a stretching vibration or a bending vibration. Okay, so usually dipole moment, change in dipole moment is the factor that decides the intensity of an IR vibrational band or a peak. Okay, so the greater the change in dipole moment associated with the vibrational transition or vibrational motion, the greater will be the observed IR vibrational peak intensity. Okay, so the lesser the change in dipole moment, the lesser will be the intensity of the IR vibrational peak. So usually stretching vibrations causes a greater change in dipole moment compared to bending vibrations. So you can say that stretching vibrations gives rise to much more intense peaks compared to bending vibrations. Okay, another factor that could influence or affect the intensity of higher vibrational peaks is that the electronegativity difference between the atoms involved in forming the chemical bond. Okay, so the greater the electronegativity difference between the atoms that forms the chemical bond which undergoes vibration, the greater is the dipole moment between the magnitude of the dipole moment set up by these two atoms. Okay, so the greater the electronegativity, the greater the dipole moment. Okay, so the greater would be the change in dipole moment when the atoms vibrate or oscillate. Okay, so the greater the electronegativity difference, the greater would be the intensity of the IR vibrational peaks. Okay, so the lesser the electronegativity difference between the atoms that forms up the bond that vibrates, the lesser will be the intensity of the IR vibrational peaks. Okay, so that is a rule of thumb. And then you can characterize or classify peaks into three categories based on the intensity of these peaks. Okay, So the peaks that has got greater intensity, okay, so that means the peaks which has got a transmittance in the range of 0 to 35 percentage, because the greater is the absorption, the lesser will be the transmittance. Okay, so the lesser the transmittance, the stronger would be the peaks. So these peaks can be classified into the strong peaks, and these peaks can be represented by S, okay, which stands for strong. And if the transmittance is of the peaks is in the range of 75 to 35 percentage, the peaks absorb the IR radiation to some medium extent. Okay, so such peaks will have medium intensity or medium peak height, so they can be represented by the small letter m. M stands for M in medium. And the lesser the absorption, the greater would be the transmittance. So if the transmittance falls in a range of 90 to 75 percentage, the peaks can be the peaks can be classified as weak peaks, which is being represented by W. Okay, and you can have, in addition to this, if you start to look at the shape of the vibrational peaks, you could see either narrow vibrational peaks or very broad vibrational peaks. Okay, so very broad vibrational peaks could happen because of several reasons, such as hydrogen bonding, okay, proton extension, those kind of phenomena, and which we shall be seeing later. So why are we, as I asked before, why are we interested in IR spectroscopy? Okay, because again I must re-emphasize that IR spectroscopy deals with the interaction of IR radiation with the bonds, the chemical bonds in a molecule. Okay, and it is these chemical bonds that forms the molecular structure. IR spectroscopy can be used as a probe to, or can be used as a tool to probe the molecular structure of the molecule. Okay, and here is some interesting fact. Say for example, if you consider C double bond C bond and C double bond O bonds, carbon and oxygen vary in their electronegativity to a little extent. So mostly these two types of bonds have somewhat similar character, electronic character, and somewhat similar dipole moment. So these bonds will, the vibrations associated with these bonds will show peaks in almost similar regions of the IR spectrum. Okay, similarly CH and NH, because carbon and nitrogen are also close to each other in electronegativity scale, these two bonding CH and NH vibrations will also show up their IR spectral peaks in a close proximity. Okay, okay, so when a suitable radiation falls upon, IR radiation falls upon on an organic molecule, several of its chemical bonds can interact with the IR radiation, provided that the IR radiation is of a suitable frequency to bring about a vibrational change in the interacting chemical bond. Okay, so for example, if you consider phenol has got carbon single bond, carbon double bond, then carbon hydrogen single bond or sigma bond, and carbon oxygen sigma bond and oxygen hydrogen sigma bond, right? So all these the different types of bonds, okay, carbon single and double bonds, carbon hydrogen single bonds, carbon oxygen single bonds, and oxygen hydrogen single bonds differ in terms of the nature of the atoms involved in bonding, as well as the electronegativities of the atoms involved in bonding, right? So obviously the frequency of vibration of these bonds, carbon single, carbon double, carbon hydrogen single, carbon oxygen single, and oxygen hydrogen single bonds would be different. Okay, so mostly the bonds that is being associated with, or the bonds that represents the entire molecular structure, for example in phenol, OH is a functional group. Okay, and but the phenyl system has got carbon single and double bonds, and carbon hydrogen single bond. Okay, so these bonds represents the almost 80% of the nearly 80% of the molecular structure, and this the vibrations associated with these bonds, carbon carbon bonds as well as carbon hydrogen bonds, mostly falls in a region of 400 to 1300 centimeter inverse. Okay, so uh, this region, the region between 400 to 1300 centimeter inverse, in which you can observe the bonding vibrations associated with the bonds that characterize or represent the almost the entire molecular structure, is called a fingerprint region, because the vibrations in this particular region, fingerprint region, is something like the fingerprint identity of the entire molecular structure. Okay, so in this region you can find the carbon hydrogen bending vibrations from say 450 centimeter inverse up to 900 centimeter inverse, and NS bending vibrations, then carbon carbon stretching vibrations from 800 centimeter inverse up to almost 1200 centimeter inverse, then carbon nitrogen stretching vibrations, then carbon oxygen stretching vibrations. So almost all these stretching vibrations, if you start scanning the molecular structures of organic molecules, you must be able to, or you must already be knowing that these kind of bonds usually make up almost the entire part of the molecular structure of an organic molecule. Okay, but the region starting from almost 1400 centimeter inverse right here up to say 4000 centimeter inverse is being usually associated with uh, the vibrations of chemical bonds involved in functional groups such as OH, hydroxyl functional group in phenol. Okay, so this region, the region from 1400 centimeter inverse to 4000 centimeter inverse, is called the functional group region or group frequency region. Okay, so we have got if you see this graph, you can see that the vibrations of carbonyl functional group, okay, OH functional group, NH functional group, and this type of functional group vibrations can be identified in this functional group region. Okay, so it's easy to then based on this classification, it's easy to identify a type of vibration and whether this vibration belongs to the entire almost the entire molecular structure or towards or belongs to a functional group of the molecule. Okay, so this spectrum will give you an illustrative idea of this the classification of vibrational transitions associated with the typical types of bonds. Okay, so the region from almost 600 to 1600 centimeter inverse is usually associated with the vibrations of single bonds, for example carbon carbon, carbon nitrogen, carbon oxygen single bonds. So this falls in the fingerprint region. So almost from 600 to 4000 centimeter inverse, we have got the functional group or group frequency region, where in which the energy region or spectral region from 1600 centimeter inverse up to almost 2000 centimeter inverse is being associated with the vibrations of double bonds, okay, such as the ones in carbonyl system, C double bond and C double bond C, etc. Okay, then the region from 2000 to 2700 centimeter inverse is basically dealing with the vibrations of triple bonds, such as the ones here, C triple bond C, C triple bond N. Okay, and the region starting from 2700 up to almost mostly up to 3600 centimeter inverse basically deals with the vibrations of bonds which involves a hydrogen atom such as OH, NH and CH. Okay, so you can rationalize this the location or position of the vibrational bands associated with this typical bonds with the force constant of the bonds as well as the reduced mass of the involved nuclei. And if you see this two spectra, okay, so here this spectra is basically IR spectrum deals with this typical molecule, okay, and this spectra deals with the aspect of the typical molecule, okay. So in here the only difference is that in this particular carbon we have got a CH3 which is absent in this typical molecule, so that is the only difference, okay. So but you can still see that the IR spectrum looks almost similar except to a few minor differences in the fingerprint region which deals with the molecular structure, okay. So here you can see that CH stretching happens at almost the same energy here in both the molecules, whereas CH bending also happens at almost the same frequencies or energies for both the molecules. So what will be the type of molecular system? You can see from this example that a typical vibration, okay, unless it is being influenced by some other factors, external factors, usually gives rise to a IR peak at exactly the same position, okay. So in other words, the vibrational energy of a typical bond, okay, would be unique.